All right, folks. Let's go ahead and let's get started. Let me set the timer here. I want to start by apologizing for this afternoon. There is an issue with my internet. I'm hoping right now that the issue has been resolved and that the video will come through okay. Let's keep our fingers crossed and hopefully that it'll work out for the best. But again, I apologize for that. And let's go ahead then. And what I'd like to do then is I'm going to get started. I want to review. I want to go ahead and I want to talk about the part that hopefully we were able to get through most of the lecture today, and before the internet starts cutting out. And so I'm going to pick up here with the discussion of basis. So let me go ahead and share my screen with you. And I want to start there. If there were parts of it beforehand that were that cut out and you weren't able to get, please make sure that you ask about it on Thursday, and we'll go over it then. Okay. But I do want to start then with the discussion of bases, and then we'll pick up. We'll start from there. Okay. So we finished up talking about acids. We talked about equilibrium involving acids. We defined acids. We were able to work through problems and calculations involving both strong acids and weak acids. What we want to do now is we want to turn our attention to bases, okay, and the second category of compounds here that we want to talk about. So a base is a compound defined by Arrhenius as being a contributor of hydroxide ions. So Arrhenius defines a base in a very specific way, much the same way that he defined an acid in a very specific way. So with an acid, with the Arrhenius acid, it's any compound that can contribute a hydrogen ion. With an Arrhenius base, then it is any compound that's going to contribute a hydroxide ion. Okay, so those are the key differences there. So only compounds that can contribute a hydroxide ion will be considered a Arrhenius and Arrhenius base. So for example, lithium hydroxide here, sodium hydroxide, all these here are hydroxides. These are the metal hydroxides. You have alkaline metal hydroxides for the first three, and alkaline earth metal hydroxide for the second one. Okay? So, but they all can contribute hydrogen ions, which means that what it means by contributing hydrogen ions that it ionizes completely. These are all very strong bases, and you have the list of strong bases and strong acids, folks. And so make sure then that you memorize that list. Okay? But the reason why these are considered strong bases is because when they dissociate, and we'll take sodium hydroxide here as an example, when they dissociate, okay, they dissociate completely. We have almost 100% dissociation with very little going back at equilibrium. And so therefore, when it dissociates, we form then the sodium ion and the hydroxide ions, and it's the production of this hydroxide ion right here then that makes sodium hydroxide, at least according to the Arrhenius definition, a base. Okay, and so this represents then a nearly almost 100% dissociation. Now, almost, not quite. You can never. You can no. Obviously, we can never get a 100% dissociation, but that's in very much the same way that the high percentage for an acid defines in a strong acid, a high percentage of dissociation for a base defines in a strong base. Okay, so there it is. So all of these bases that I provide for you here defines in a strong base. So that is the definition given by Arrhenius. Okay? Now we'll talk about the Bronsted-Lowry acid-base theory, and we'll use that much more as we move forward and we talk about equilibrium involving bases. But make sure you remember then that the way that Bronsted-Lowry defined a base was then any compound then that can accept a hydrogen ion from another compound. That means then it broadens in very much the same way that the Bronsted-Lowry definition broadened the definition of what we could consider an acid. The Bronsted-Lowry definition of a base broadens what we will consider then as base. So bases now aren't only compounds that can contribute hydroxide ions, but it's any compound that can accept then a hydrogen ion from some other compound. Okay, so those are the two definitions of bases that we will be working with. Now we saw then with bases some other characteristics of a base then, and this is at 25 degrees Celsius. A basic solution then is going to have a pH that's greater than 7. The pH that's going to be greater than 7. So on the pH scale, if you have a number greater than 7, you have a base. Okay? All right. Now, we also talked about then how we can calculate for what's called the POH here. The POH, and remember this P here ends up representing an operator that tells you to take the negative log of what follows it. And so therefore, to obtain the POH, we take the negative log of the hydroxide ion concentration. Now, why would we need the POH? Well, if we wanted the pH, and remember the definition that the relationship that I provided for you here earlier on, if we wanted the pH of a solution, now, we could easily work with a POH. Now, that's fine. But a lot of references indicate the pH rather than the POH. And so if we needed the pH, okay, then what we can do then is we can go ahead and if we have the hydroxide ion concentration, we can calculate the POH, subtract that from 14, which remember is the pKw, and we can get the pH from that. Okay. All right, so that's really the basic definitions and that we will work with as we go through these problems here. Okay, and so that's where I started it this afternoon with you. I'm hoping then that I can provide a little bit more clarity here for you as well. But unfortunately, like I said, with the what was going on with the internet, I wasn't able to present this more clearly to you. So hopefully, it's clear now what a base is as we move forward. We'll talk about the difference between a strong base and a weak base in just a moment, but the strong base, then we have 100% dissociation. So let's go ahead then, let's do a quick calculation involving strong base. Okay? Now, there it is, there's our sodium hydroxide. Okay, there's our sodium hydroxide. And so let's go ahead then, and remember, if sodium hydroxide being a strong base, what it means then is that we get nearly 100% dissociation. What we have to make sure we are clear on here then is that the equilibrium will shift far to the right, which means then once sodium hydroxide dissociates, we will have in solution sodium ions, okay, and hydroxide ions. Okay. So therefore, the main species, the primary species in solution right now at once the dissociation occurs, the primary species that are floating in solution then will be sodium ions and hydroxide ions. And we can also say then water. Okay, all right. So therefore, if you want to consider what we talked about last week, there's a secondary process that occurs as well. There's a secondary process that occurs as well. That secondary process will be then the autoionization of water. Okay, so we have that happening, but we also have the autoionization of water occurring as well. Okay, and so when we take a look at this equilibrium here, this equilibrium here does contribute hydroxide ions. So let's go ahead and let's consider that. So the autoionization of water not only contributes hydrogen ions, but will also contribute hydroxide ions. And so we have two sources of hydroxide ions. We have then the dissociation of sodium hydroxide and the autoionization of water. Okay, all right. So with that said, then let's go ahead and write down what we have here. So we have then a 1 times 10 to the minus 3 molar solution of sodium hydroxide, which means then at equilibrium, we're going to have 1 times 10 to the minus 3 molar concentration of sodium ions. And we'll also have a 1 times 10 to the minus 3 molar concentration of hydroxide ions. For water here at equilibrium, then we're going to have 1 times 10 to the minus 7 molar concentration of hydrogen ions, and also 1 times 10 to the minus 7 molar concentration of hydroxide ion. So if you take a look at this, the primary source of hydroxide ion then will be from this dissociation right here. Okay. This dissociation gives us a hydroxide ion concentration that is close to 100,000 times greater than that from this dissociation. So if we're going to find the pH, okay, if we're going to find the pH, the primary source of ions will be from this dissociation here. Very little from the autoionization of water. Okay, so we are going to work primarily. The calculation will involve primarily this equilibrium right here. All right. So let's go ahead and let's work this out. So if we're going to try to find the pH, we don't have any pH here. There's no hydrogen ions that appear in this equilibrium. The hydrogen ions here, we have hydrogen ions in this second equilibrium here, but it's so small that doesn't exist. It doesn't factor into our calculation. Okay? However, we do have a source of hydroxide ions. So we do have a source hydroxide ions. So what we can do then, and this is what I was trying to draw your attention to, the previous slide. What we can do then is if we can calculate for the POH, if we can calculate for that, we can find then the pH. Okay, so the negative log of the hydroxide ion concentration, which we do have, I'm sorry, hydroxide ion concentration, which we do have right here. Once we plug this in here, we can go ahead then and calculate for the pH, okay, because then we can just take our POH and subtract it from the pH. Okay, so let's go ahead then and let's solve for the POH, and so this is how we'll work it out. So the POH then will be the negative log of the hydrogen ion concentration. And remember, the primary source of hydrogen ions. So if we had a very dilute solution here, that generated a hydroxide ion concentration that was less than 10 to the minus 7, then our solution will be neutral. We did a problem very similar to that last week. And so please take a look at that and realize then that we have to compare the concentrations here. Okay. All right, so with that said, let's go ahead and plug this in here. We have then 1 times 10 to the minus 3 molar, which gives us then a POH of 3. Okay. So it's going to be 3.00, okay, and that's our POH. With our pH then, again, the problem's asking for pH, so POH, don't stop here. And what I was trying to point out to you in class today was that there's a common mistake that students, new students make to this, and that is they will stop here and they will see then 3 and then write down the answer then as pH of 3. Now, folks, don't get caught in this trap, because if you think about this, then we have a basic solution. If you have a basic solution, the pH cannot be 3, because remember, we talked about this, and I was trying to point this out to you in class today, that if you have a pH that is less than 7, then you have an acidic solution. And here you have a pH that is 3, that's less than 7. But this cannot be your answer, because this is a basic solution. And a lot of people make this mistake because they forget that what we solved for here was not the pH. What we solved for here was the POH. And so therefore, this cannot be your final answer. Okay. All right. So with that said, then remember, our answer has to have a pH that is greater than 7, because it's a solution that has a pH of greater than 7 is a basic solution. And again, the pH of 7 equal to 7 is our neutral solution. So we should not expect a pH that's equal to 7, but we definitely should not be looking for a pH that is less than 7. All right, so to calculate for the pH then, what we have to do then is take our answer, the pH that we've calculated for here, and we have to subtract it from 14, and there we get our answer then as 11. So that makes more sense right here, you guys. That makes more sense right here, because this pH then is greater than 7. So there is our final answer, and that's something you want to make sure you check for as you work through these, okay, as you work through these problems. All right, let me go ahead and save that problem for us. What I'd like to do, and so let's go ahead then, and let's take a look at the next problem. And so this is the problem that I left you with on yesterday, okay? And there's the answer. This is number 8 from your problem set. What I would like you to do, I would like you to get out a piece of paper, and what I'd like you to do is show me how you would calculate the pH of this solution here, of a calcium hydroxide solution, okay? And then make sure then that you show me your work, and make sure you post your work to the Google Classroom like we've done before, so I can see how you do this. So let's take about let's see here. Let's take about 3-ish minutes. Take about 3 minutes to work through this problem here, and show me then what is the pH of this solution here that is made up of 1.0 times 10 to the minus 3 molar solution of calcium hydroxide. Okay, so 3 minutes. Let's work this out. And then we'll go over together. Okay, go ahead and take 3 minutes. Okay, let's take a look at this, you guys. Let's take a look at this here. Now, let's consider the 2 equilibria that are occurring here. So calcium hydroxide, again, you should be able to recognize that calcium hydroxide is a strong base. So therefore, the dissociation then of calcium hydroxide is going to be, aqueous. So this is a strong base, okay? So we have very little going back. And so therefore we almost have 100% ionization, which gives us a calcium ion and 2 hydroxide ions. And I think for many of you, if there was a mistake that's made, it's made right here. Okay? You forget, first of all, that you forget that this is the formula for calcium hydroxide, and you got to get that right. If you don't get that right, this whole problem is going to be wrong. Because if you don't get this right here, you're going to fail to see then that you, for every 1 calcium hydroxide molecule, you will generate, as it dissociates, two particles of hydroxide ions. You got to remember that, and this is critical. In just a moment, you're going to see why when I asked this problem in the past, a lot of students make the mistake because they forget that this is a 2 normal solution. Okay, so calcium hydroxide is going to be a 2 normal solution because it can generate 2 hydroxide ions. Okay, all right. So keep that in mind, and let's continue on here with our analysis. Okay, because the second process then that occurs in this reaction, the second equilibrium that we find here then that will generate hydroxide ions is the one autoionization of water. So autoionization of water, let's go write this down. We get then hydrogen ions, okay, and hydroxide ions. So there it is, the second source of hydroxide ions. Okay. All right, so we have then a 1 molar 1 times 10 to the minus 3 molar solution of calcium hydroxide. When it dissociates, it will form then a 1 times 10 to the minus 3 molar of calcium ions, and 2 times 10 to the minus 3, 2 times 10 to the minus 3 molar hydroxide. And again, this is where you have to be careful. We have double the amount of hydroxide, so the concentration of hydroxide, and that's what we want, it's going to be double that what we start out with here. Okay. All right, so down here, then the second equilibrium, we only get 10 to the minus 7 molar of hydrogen ions and 1 times 10 to the minus 7 molar of hydroxide. So again, the primary source of hydrogen ions then will be from the dissociation of calcium hydroxide right here. So that's going to be our primary source of hydroxide ions. Hydroxide ions. Okay. All right. So the primary species floating around, and again, you don't have to indicate this when you do this, but just for right now, I'm going to keep writing this down to make sure you remember this. Okay. So in solution right now, what we have in solution then will be, and I'm going to will be calcium ions. We're going to have calcium ions floating around. We're going to have hydroxide ions floating around from that dissociation, and we will have water. Okay. Those are the primary species floating around in solution here. Okay. All right. The rest of this then is pretty much exactly like the problem that we did previously, the sample problem. The only difference then is this right here. This is going to be where I suspect then that many of you will make your mistake. I'll take a look at your work. Okay. So this is where you will, in the past, I only say that because in the past, many students make the mistake. Hopefully you don't, but like I said, I'll see when you submit your work. Okay. And so please don't change anything. If you want to take notes on this, you can, but don't change anything. It gives me an opportunity to see then how many of you get this or how many of you are not getting this. Okay. All right. So with that said, then we're going to go ahead and we're going to calculate for then the POH, just like we did previously. Okay. But I'm going to point out to you that there is a second method that we can use to get our answer. Okay. And I'll show you that in this problem as well. Okay, so let's go ahead then. We're going to find the POH first. Okay, so the negative log of the hydroxide ion concentration, which this time is 2 times 10 to the minus 3 molar. And so if you plug that in, then the POH is going to be equal to I get here 2.70 okay, as the POH. Okay. All right, so with that said then, in order to find the pH, the second half of this one, then we're going to take 14 and subtract 2.70 from that, and then we get our final answer that's 11.30 as the pH of this particular calcium hydroxide solution. Okay, so that's what we have right there. All right, the second way they can go about solving for this one. Okay, the second way you can go about solving for this one, and I'm just going to highlight for you, and I'll leave it up to you to solve for it. If you're interested, if you want me to work this out for you, stop by or ask me on Thursday. But the second way that you can solve for this one, then, is since we have the hydroxide ion concentration here, we can calculate for the hydrogen ion concentration, remember, because we know then that the ion product constant, okay, divided by the hydroxide ion concentration, that'll give us the pH. That'll give us the pH. Once we have the pH here, once we solve for this, so you'd plug in 2 times 10 to the minus 3 here. Okay. Once you have that, it's a matter of taking the negative log of the hydrogen ion concentration, and you should end up with that same answer anyway. Okay, so 2 different ways you can go ahead, go about solving for this one. Completely up to you how you want to do this. Okay. All right. Very good. So that's with a strong base. Solving for the equilibrium problems involving strong bases, pretty straightforward, not that difficult. I hope you can, well, you'll be able to work through this. Okay, so the homework that I will assign for tonight is going to give you a chance to practice this as well. Okay? But we want to also be able to deal with the weak bases. Okay? How do we deal with equilibrium involving weak bases? So the weak base equilibrium, okay, is not like the strong base equilibrium, because the percent association is going to be very small, which means equilibrium is going to favor the reactant side of things, the reactant side of things. And so how we want to approach this is we want to imagine then the weak base then as interacting with water. We can define that equilibrium by the equilibrium constant that we refer to as Kb. Kb is the equilibrium constant for weak base, for bases, okay, and Kb for strong bases, just like Ka is for strong acids, are going to be much greater than 1. Okay, so make sure you keep that in mind. That we don't. It's rare that we can define the Kb for a strong acid, but I'm sorry, for strong bases. But for strong bases, okay, Kb tends to be much greater than 1. In much the same way that with strong acids, the Ka was much stronger, much greater than 1. So the larger the Kb, the stronger the base. And so we can use the equilibrium constant here for exactly the same thing to determine and compare then the strengths of bases. Okay, so this is how we want to imagine this. Okay? So it's the interaction with water. It's the interaction of water that we want to take a look at, and so we can set up the law of mass action for this process, this equilibrium as well. And so with that said, then Kb is going to be equal to here the. I'm sorry. Let me do this first. Okay. So with that said, let's go ahead and identify the acids and bases here. So if you notice here, in this process, cyanide and water form then hydrocyanic acid and hydroxide here. Okay, so if you notice here, what's happening is that cyanide is picking up a hydrogen from here. It's accepting a hydrogen from the water, which makes cyanide here then the base. Okay, and water in this case, since it is donating its hydrogen to the cyanide, that will be your acid. So water here is serving as an acid. So therefore, when we get to the right-hand side, hydrocyanic acid here. So this is going to be your conjugate acid here, and here is your conjugate base. Okay, all right. Now we know then that the hydrocyanic acid is a weak acid. Okay, but we know then also that the hydroxide is a very strong base, and it's for this reason here that the reaction will shift. And I'm sorry, don't mind the arrows here, but the reaction will shift way to the left, way to the left. Because cyanide is a much weaker base than hydroxide. Cyanide doesn't do as good of a job as taking a hydrogen from water as hydroxide is taking hydrogen from the hydrocyanic acid. And because of that, the equilibrium highly favors the left. We expect then that cyanide then is going to be a very weak base. Cyanide is going to be a very weak base, much less than 1. Okay. All right. So with that said, we can go ahead then and set up the law of mass action for this process here. And if we could get the concentrations here, we can solve for it. Okay. So it's going to be then the concentration of HCN over the concentration of hydroxide times the concentration of hydroxide. Okay, so there are your reactants, okay. And the product then is going to, I'm sorry, the product and the reactant then is going to be just cyanide in the numerator. Why? Because remember, pure liquids, we don't include that. Okay, so that is going to be then the law of mass action specifically for cyanide. Okay, for this is the and this will give us Kb for cyanide, and we expect then Kb for cyanide here to be less than 1. Okay, so just doing a quick analysis, that's what we should expect here again. So make sure you can see then from my analysis here, why we can predict that Kb is going to be less than 1. Again, the reason for that, hydroxide here is much stronger than cyanide. We're just comparing the two bases. Hydroxide is much stronger than cyanide. It will remove the hydrogen here and send the reaction back towards the left. Okay, and that's where equilibrium lies. It lies far to the left. All right. So with that said, that's for the specific cyanide acid, a cyanide base. Is there a general formula we can use for bases in general? Okay, and there is. Okay, so I'm sorry. Let me go this here. I have it right there for you. Okay. All right, and there is. We can go ahead and we can define then a generic process that can be used for all bases, and it's this right here. B then is going to be the base. Okay. And the base then here, and let's go ahead and write this in. The base here then is going to accept a proton from water here to form then here your conjugate acid. And this is the generic form of the conjugate acid, a generic formula for any generic acid. And it will form then hydroxide, which is going to be considered the conjugate base. So for all weak acids, this is the process that we expect to Okay, this is the process that we expect to get for weak. I'm sorry, not weak acid. For weak bases, this is the general equilibrium expression for any weak base, and therefore then the equilibrium, the law of mass action for this general base that is going to be this right here. Okay, and it'll be, and this is what we'll use. And again, for all weak acids, we expect in Kb to be less than 1. Okay. All right, let me go ahead and erase this really quickly so that you can see what we have here. So this is conjugate acid and conjugate base. Okay, let me save that for you. Let's go ahead then and let's take a look at some values for Kb. Let's take a look at some values for Kb. And again, like I told you, Kb can be used to compare bases. So the larger the Kb value, the stronger the base is going to be. So if we take a look at these 5 weak bases here, you can see then this is the formula for the base. This is the formula for the base. We'll talk about what these amines are in just a moment. Amines are organic bases in organic chemistry. We'll talk about that. But if you notice here, there's ammonia right there. All right. So with that said, the larger the value for the Kb, the stronger the base is going to be. So if you take a look at this then on our list here, ethylamine then is going to be the strongest of the bases for all of these bases here. And if you take a look at this then, using the same logic here, aniline is going to be then your weakest base. So we can go ahead then and we can use the Kb values to compare bases, the strength of bases, and in much the same way we use Ka values to compare the strength of acids. Okay, so that's one important thing that we can use Kb's for. Okay? And so we can also use Kb's then, if we know it, if we're given, we can find these reference values, we can use Kb to calculate for the pH of a solution in much the same way that we did for the strong bases. Okay? We can calculate for the pH of a solution, and the method for a weak base, and the method we use to solve for that pH is going to be identical to what we did for solving for the pH of a weak acid. So again, in order to find the pH for a weak acid, we had to use the ICE table to find the pH, the hydrogen ion concentration for the solution, and from that we can calculate for the pH. For weak bases, what we would have to do then is we would set up our ICE table to find the hydroxide ion concentration. From that, we find either the POH or the hydrogen ion concentration directly, and then from there we can get the pH. Okay? So with that said, then it's going to be ICE again. It's going to be using the ICE table to solve then for these problems. Okay, so let's go ahead then. Let's take a look at an example. Okay? All right, so we have then a solution of ammonia. Okay, so the first thing you want to do then, just like what we did with the weak acids, okay, we want to make sure then we write down and identify the processes that are occurring, okay, that will generate for us the hydroxide ion concentration. So the very first process here is going to be then ammonia. Okay. and it's going to be in water. So that means it's going to be reacting with water. So remember the general formula that we're going to be using here, you guys. The general formula here is going to be the base plus water is going to give us, okay, the conjugate acid plus hydroxide. You want to make sure you keep this in mind as we work through this, okay, as we work through these problems. Keep this in mind that this is the equilibrium, the general equation for the equilibrium. Let's go ahead then and let's apply this to ammonia. Okay. All right, so here's water. The equilibrium here is going to highly favor the left-hand side because ammonia is a weak base. Okay, and so therefore then, ammonia is going to pick up a hydrogen from water to form the ammonium ion and hydroxide ion. So that's what we have. That's the very first process that will occur. Now we also have, remember, water. Water is going to be at equilibrium, the autoionization of water. We're going to have this process occurring as well. That will also generate hydroxide ions. So both of those processes will generate hydroxide ions. Okay, and so therefore, let's make sure what we have here. The primary species floating around in water right now, floating around in this solution right now is going to be undissociated ammonia, okay, and water, because this is going to be very small. Look, KB here, and let's go ahead and take a look at this. We have our value for KB. KB for ammonia is going to be 1. Sorry, let me go ahead and write this down. KB then is going to be 1.8 times 10 to the minus 5. That's a pretty small number. So KB for ammonia is 1.8 times 10 to the minus 5. And so therefore then, in order to find the pH of the solution, we're going to have to find the hydroxide ion concentration for either one of these. So we already know what the hydroxide ion concentration for the second equilibrium is. It's going to be then 1 times 10 to the minus 7. Okay, for either one of those. Okay, so if the hydroxide ion concentration from the first equilibrium is less than 10 to the minus 7, we know then pH is simple, has to be 7. Okay, but we are told here that we have a 2 molar solution. Okay, which means then when this dissociation does occur, we're going to have a 2 molar solution of ammonium and a 2 molar solution of hydroxide, possibly. Okay, that is if it were a strong base. Okay, the mistake that is commonly made here is that the automatic assumption is that that's what we have here. That's not the case here, you guys. We cannot assume that because this is not a strong base. And so what do we have to do? We have to set up our ice table. So let's go ahead then and let's set that up, and then we have to solve for it. Okay. All right, so with that said then, let's go ahead and set it up. So the equilibrium here is going to involve then ammonium, NH4, NH4 plus OH minus. Setting up our ice table. Okay. We're going to have then a 2 molar solution of ammonia. We don't have to worry about water at all. Water is a liquid, okay, so that's not going to be involved in this. And initially then 0 and 0. We know then in this case then, and we got to make sure we keep this in mind, that we keep doing this. We know then that let's see here. Q, if this case, then Q is going to be less than K. Why do we need to know and remind ourselves of this? Because then we're going to lose some from the left-hand side and gain the change, add change to the right-hand side. So therefore, at equilibrium, we're going to have this much ammonia left, and we're going to have this much ammonium and this much hydroxide. Okay. Look familiar, you folks? Looks familiar? Let's go ahead, then it should. So let's go ahead and finish solving this problem here. We have then setting up the law of mass action with everything plugged in correctly, 1.8 times 10 to the minus 5, okay? And that's going to be equal to x squared over 2 minus x. Okay. All right. So x then, if you plug everything in, again, we're going to assume the 5% rule here. Okay. So we're going to assume the 5% rule here. So the 5% rule at this point, then we're going to assume it's going to be workable. This is 10 to the minus 5. This is 10. This is 10,000 times larger than the KB here. And so therefore, ignore the x on the bottom here. If we do that, then we can, x then is going to be, if we solve for this one, 0 0.0060. Okay, and so with that said, this is going to be equal to the hydroxide ion concentration. Okay, now you can check, plug this back in, compare these two. Remember, get the ratio for these two here, multiply it by 100, and you can see then the 5% rule does work here. So the 5% rule does work. Okay. Sorry, I'm running. Okay, so 5% rule works here. And let me go a little bit over time here. So the 5% rule works. So with the hydroxide ion concentration here, we can go ahead then and we can solve for the POH, which I'm going to ask you to do. So therefore, the POH is going to be then 2.22. That's the POH. You can't stop there, you guys. You can't stop there yet because we got to find the pH. And so I'm going to leave it up to you to find the pH. So please make sure, if you cannot, make sure you ask me, take this and subtract 14. And so therefore our answer then is going to be 11.78. That is our answer. So we got to take that next step here to find then the final answer as 11.78. Okay, so please make sure then that if you're not quite sure how to get this, combine and ask about it on Thursday. Make sure you ask about it on Thursday. And then also, we'll go over this. Okay. So again, if you're not quite sure about the 5% rule, ask about that as well. Okay. But this then is our final answer for this particular problem. Okay. All right. Very good. So please make sure, and I'm going to go ahead and sign. I think it's set D for chapter 14 here. Please start working on that. Okay. And then if we have some time on Thursday, I'm going to try to work through a few of those problems here. I was hoping that we can get more covered today, but it doesn't look like we'll be able to meet up with our goal. So if we have to push back the exam date from Monday to next Tuesday, from next Monday to next Tuesday, we'll go ahead and get that done. Okay, but again, we didn't quite cover much in class this morning either because of the I'm sorry, this afternoon either because of the internet issue. But things will happen like that. So let's try to remain flexible, and then we'll move forward with this. Okay. All right, very good, folks. I hope you have a good rest of your Wednesday, and I'll see you tomorrow in class. Okay. All right, I'll talk to you later. Bye.